Good day everyone. Myself Vaidehi working as assistant professor in Sri Muthukumaran Institute of Technology in EC department. Today the video lecture is from the subject EC3452 Electromagnetic Fields. The topic is from the Unit 1 Introduction Unit. The topic we are going to see is vector calculus integral theorems, exploring the fundamental relationships between divergence, curl, Stokes theorem and null identities in vector calculus. These concepts are essential for understanding electromagnetic phenomena and field behaviors. Next we see about the introduction to the vector calculus. Let's start with the fundamentals. Introduction to vector calculus properties. The gradient of a scalar field del f measures the rate and direction of its fastest increase pointing toward maximum change. Divergence del dot f quantities that net flow or source strength of a vector field at any point in space. Curl del cross f captures local rotation or swirling strength, revealing circulation behavior. These three different operators form the mathematical foundation for integral theorems that connect local derivatives to global integrals across regions and boundaries. Next we see about the divergence theorem. The divergence theorem is also known as Gauss theorem. Think of it as a conservation law. The net source strength generated inside a volume equals the total flow across its boundary. Mathematically, the total flux of vector field F flowing outward through closed surface S equals the volume integral of divergence of F throughout enclosed region V. The formula is integration of f dot ds equal to triple in volume integration of del dot f into dv, where n is the outward unit normal. Key applications include fluid dynamics, continuity equations, electromagnetic Gauss law, heat transfer, and mass conservation in engineering systems. Next, we visualize the divergence. To visualize divergence, positive divergence at sources shows vector always across spreading outward, including expansion or field line creation. Negative at sinks shows convergence, representing compression. Zero divergence for incompressible flows means no net sources or sinks, like in magnetic fields. These patterns help intuit how fields behavior in physical systems. Next we see about the curl of the vector field. Now curl of vector field, the operator measures infinitesimal rotation at each point, producing a vector perpendicular to the rotation plane. Its direction follows the right hand rule for the rotation axis and magnitude shows spinning strength. Real world examples include whirlpools or tornadoes where velocity fields exhibit strong curl proportional to angular velocity. The formula is del cross f is equal to dou fz by dou y minus dou fy by dou z, dou fz by dou z minus dou fz by dou x. Next we see about the Stokes theorem. The boundary curve C is any closed loop like a wire circle. Surface S spans it. Multiple surfaces work since result is identical. Circulation equals curl flux. Work around C matches vorticity penetrating S. In fluids, loop calculation equals vorticity flux through any bounded surface. The mathematical statement shows integration of f dr is equal to square surface integration of del cross f n into ds, where C is the closed surface bounded surface S and n is the normal vector and S oriented by the right hand rule. Next we visualize the Stokes theorem. The Stokes theorem in the boundary curve C is any closed loop like a wire cycle. The surface S spans it. Multiple surfaces work since the result is identical. The circulation equals curl flux. Work around C matches vorticity penetrating S. In fluids, loop circulation equals vorticity flux through any bounded surface. In the boundary curve C, any closed surface in space that forms the edge of a surface. For example, a square circular wire loop or an elliptical curve on a sphere. Next we see about the null identities. The null identities, the curl of a gradient is 0. Gradient fields are irrotational. No swirling. The divergence of curl is 0 and the curl fields are source free, only the loops. These ensure consistency with consequences like conservative forces doing no net closed path work, no magnetic monopoles and Helmholtz decomposition. Finally, the summary of the lecture. In summary, the divergence theorem connects surface flux to volume divergence for boundary flows from sources. Stokes links boundary circulation to surface curl. Null identities like del cross del F is equal to 0 and del cross F is equal to 0 to maintain the consistency. These are vital for electromagnetics, fluids, heat and engineering analysis. We came to the end of the lecture. Thank you.